I'm pretty sure everybody got 8 right. It is negative, so I'm smiley face if you said that. Anyone? I'm pretty sure I saw negative on most of the board. It's going from gas to solid and liquid. Definitely disorder is going down. It's getting more organized. But any questions on entropy?
Is it enough to prove it to say like because it's an exothermic reaction, the energy loss makes it more stable?
No, because you can have exothermic reactions that actually do get more. So it really should be based on what's happening to the molecule.
Oh, that would make a lot of sense.
Yeah. I'm glad you bring that up though, Aiden, because someone did that last period too, where they went strictly to the equation. And the equation's helpful for delta G, but for individual things, it's not always guaranteed to be one way or the other. So yeah. Okay, B says, which factor, alright, give me your attention this way. So which factor, enthalpy or entropy, provides the driving force for the reaction? Now it tells us it is spontaneous, so we know that it is happening, and since it's exothermic helps that happen, so definitely enthalpy. I should have put and or, because it could be both, but it's not entropy, because entropy is getting more organized, and that doesn't drive spontaneity. Right? So it's just enthalpy. But it could be both, right? If delta S was positive, then both of them would be driving it. But in this case, it's just enthalpy, which I think most of you have as well. So, questions on that question, though?
Can we get another smiley?
Yes, so smiley face if you said enthalpy. Okay, C, how is delta G affected by an increase of temperature? So the way I would think through this is I'd go to my equation and say, well, I know delta H is negative. And then I'm minusing temperature times something that is also negative. So it's going to be negative, right? So T, a negative T. But if T gets big,
Wait, T isn't.
Oh, it's the S that's
the
negative.
S is the, I can write that differently. So T times negative delta S. So in a sense, I have a negative, and this is going to be positive overall, right? Because I'm minusing the negative. So this ends up being positive. Now, for it to be spontaneous, what do I want delta G to be? I want it to be negative. But if this gets bigger, what's going to happen to G? It's going to get more positive or less negative, less likely to be spontaneous. Any of those answers are one and the same.
So did we get 2 smiley faces for that one?
Did you list more than one thing?
No.
Just one. We're right.
No. What if we said that it's just
Yes, increase because that means getting more positive. Yep, that's acceptable.
There's a lot of words.
Questions on C? All right, D wants us to explain why some reactions are spontaneous, but they don't proceed at a measurable rate at room temperature. So like we wouldn't see it happening, but it is still classified as spontaneous. Before I share the answer from the AP scoring guide, if I raise a hand, I'd love to hear some wording from you guys of what you think. Grant, let's hear it.
It's just mega slow, but it's still happening.
Oh, why did I miss
I mean, very valid and very true, right? That like, it's still happening, but it's just mega slow. So good, have a extra smiley face for sharing the answer. So,
One thing I remember from last class was that spontaneous doesn't mean fast.
very
So
good.
it's not like associated with speed.
Good, great connection. Good, have a smiley face for sharing.
I think like probably the value of G is like really small, but it's still negative technically, so it's still technically spontaneous, just at a very slow rate.
Yeah, I love the numerical approach of looking at it, right? Like if G is just barely negative, it is still spontaneous, but probably means it might take a while to happen. Good, and we'll take one more. Here, have a smiley face for sharing, Aiden.
Kind of like a real world example is just like the ripening of fruit. Like it's not going to happen overnight.
Yeah.
But like over time it'll gradually just.
But it is spontaneous.
Spontaneously just.
Good. Yep, I like it. If you have anything along those lines, you can have a smiley face for being correct. One thing I want to add to your explanations that I don't expect you to have done because we only briefly touched on it last time, but I want you to add it to your vocabulary when you're talking about this idea of speed and spontaneity, is the concept of the activation energy. That plays a big role with it. So just to remind you, so activation energy, right, is our little graphs back from Unit 5. Reactants, products. Give me your nice friends. So when a reaction is spontaneous but very slow, it's often because the activation energy is very, very high. So it takes a lot to get there, but it still gets there on its own accord. And that actually is a lot of times too with combustions. The reasons why combustions are spontaneous is you have to ignite them to help them get over the activation energy, but then they're so exothermic, it then like supplies the needed energy to itself. So, Sam.
So how do these spontaneously combust?
Under the right circumstances, the activation energy like is already met.
Like the sun.
Yeah, like so, like that's where like hay bales in like hot temperatures with the right amount of water, right? Those can spontaneously combust. Or like somewhere about oil rags, right? Like in a that's why you don't want to dry something that's oily because then it can combust in your dryer because of the heat. So it's obviously like under certain circumstances it would never happen, but if the outside surroundings provide it with just enough energy, it then provides its own energy to continue forward, right? So yeah, great connection.
How can something still be spontaneous if it needs energy to do it? Like, cause like if it's spontaneous, like say that that's like the big jump is there.
Yeah.
It still needs to go up really high. It's at this position. How can it like react to this position?
So I was reading about this yesterday, and I can't remember. They phrased it really well, particularly with like combustions. And I can't remember the way they phrased it, Joel. So this won't be as eloquent as the thing I read yesterday. But it's just the idea of because it's still the whole idea of gives free energy is it's free energy that can be used to do work. Right? In a combustion reaction, there is tons of energy when that reaction is happening that can be used to do work. That's what literally powers your car, is the work of the combustion, right? And so that's why it's still considered spontaneous, is because the amount of work that it releases way more work than what is needed to get it going. So you could almost look at like a net change a little bit. Yeah, it's just, and because they're so exothermic, they provide enough energy to then continually get over that activation. So you don't have to keep sparking it, right?
Okay, so then what's the difference between a non-spontaneous reaction and a spontaneous reaction?
So you can think with a non-spontaneous, it's a continual input of work to make it happen. So like boiling water is not spontaneous under normal conditions. I have to keep it on the heat continuously to make it boil. If I take it off the heat, it's not going to keep boiling on its own.
Well, like, but wouldn't that mean that under certain conditions, it still is spontaneous?
Totally, yeah. So a lot of reactions, that's why temperature is a big factor, is under certain circumstances, something that is not spontaneous can become spontaneous, for sure. Some things won't ever, like some things are never spontaneous but.
How could it like never be spontaneous? Because like, if something is never spontaneous, it just, it just doesn't happen?
Not without you doing something to make it happen.
And how so?
Meaning, like, supplying energy to it. Like, electrical energy, possibly, heat, it just depends on the reaction.
Well, like, if you're supplying heat to it, like, in a very hot environment or something, would it be spontaneous then?
I would wager, and I'll have to think about this more, I would wager that a lot of the ones that are non-spontaneous, did I start that, Kendra? Okay, I can't remember. That are always non-spontaneous under conditions, need other things besides just heat energy to work. That would be my wager, because heat is something that the environment can supply, but like electrical energy isn't something like that the environment can just like pull from.
Could like could a star like exploding be spontaneous?
Say that again.
Is a star that is exploding be spontaneous? But it's a fusion reaction, so it's getting less free, so it's low enthalpy. Oh, but it's releasing a ton of energy.
Yes. So the enthalpy outweighs the change of the entropy of it. So yeah, great question. Rachel, did you have a question?
No, I was just gonna say, we broke down about like the activation energy in our response, we get additional smiley face.
Yeah, you can. Yeah, if you run activation, then sure. Okay, oh yeah, Aiden.
Okay, guys, so like on the quiz, it's like G is really small, it's not quite 0. Or no, it's like, it's negative, but not quite 0. But like examples of that would be like metals oxidizing, right, where it's like happens really slowly, but it's still
Yeah, a rusty process for sure, right? Takes years, but it is still
technically
spontaneous. Yeah, no, great real life example. Okay, kind of going off of that, we're gonna learn about oxidation and reduction. So kind of 2 big takeaways. So these are your 2 objectives for today. The first thing is we're gonna learn how to assign oxidation and reduction. So we'll learn what those are and assign them. And then the second thing is we're going to explain a galvanic cell, which is AKA a battery. How does a battery work? Oh, let's go. From a chemical standpoint. Okay. I'll tell you right now, and I'll tell you again. One of the questions on your FRQ for Unit 9 is labeling a galvanic cell. So when we go through that process, kind of think to yourself, like, okay, if I'm given a blank one of these, could I do it myself? Okay. All right. So the idea here is, and we're going to do a demo to get us kind of a talking point. So I have solid copper wire. Everyone see that okay? Okay, so notice CU solid. Okay, I'm going to mix it with, so here if you want to label, this is the overall reaction. This is the net reaction. So if you want to label those to remind you. Okay, what does the net reaction get rid of? Spectators, right? So I'm going to mix this, or I'm going to put together copper and silver nitrate. So silver nitrate is a solution. AgNO3, it separates into AgNO3, and NO3 is a spectator, so we're going to kind of ignore it. Okay? So I'm going to pour these things 2 together. It is thermodynamically favored, because all I have to do is pour them together, and it's going to start doing their thing. Okay? So then, Isaac's reading to the left side, we are going to make solid silver. And what's going to happen to our solid copper?
It's gonna be
Aqueous.
So it's in a sense going to dissolve.
Dude.
So the copper's going to dissolve, the silver's going to... Now, this isn't alchemy. I'm not creating silver per se, because where's the silver already?
It's in there.
Yeah, it's in here, right? So like in terms of making money, we're breaking even, because I had to buy this, which is really expensive. And now I'm just pulling it out. I mean, I guess I could make money because the school bought this.
You actually like do something with alchemy, like
Well, I mean, I guess in a fusion, like, yeah, kind of actually it is real. Just kidding. It's just not called alchemy. It's just called a fusion reactor.
Dude, I'm like kind of just assuming this here. Will the silver be like a powder in the bottom?
Why would you assume that, Joel?
Because, well, like, I was thinking like it would be, like since it's solid and stuff, like I was thinking one of 2 things. Like either it would like replace the spots where the copper was, which would be really, really cool, but I don't know what would happen.
Yeah.
just makes it stick.
So it's going to come, they're like flakes, like silver flakes.
Is it like a precipitate?
It's quite pretty. Kind of like a precipitate, yeah, where it doesn't form in like a perfect cube, right? But then I could melt it down.
Is there anything that does do that?
Is this the one where you like can put pennies in there and it'll turn silver? Or is that something else?
It is similar in the sense that that's an oxidation reduction reaction. It's actually not silver when you do that. You actually are plating it typically with zinc.
Oh, okay.
But then it makes it look silver, so you call them silver pennies. But it is an oxidation reduction reaction. Yeah, it's the same type of reaction, just 2 different things. So the key to an oxidation reduction reaction. Say what?
Can you use it as like legit penny? Just like go to the store and just like hand them 100
I don't.
whatever to get $1 worth of stuff.
I don't know. I don't work at a store, so I don't know what they
I mean,
do.
that would be kind of
I mean, it's just a penny, so.
They probably
I mean,
arrest
that would be like
you.
a waste
You
of
might call
money.
somebody like, this guy's making his own pennies and they're not very good. Okay, so what I want you to label, so connect the 2 pieces, okay? And then what we need to track, the definition of a redox reaction is a transfer of electrons. So these particular reactions are, and it's weird because you'd think all reactions would involve a transfer, but they don't. For example, in precipitation reactions, they just trade partners. But this thing's positive, this thing's negative, and then they just trade. But there's actually no transfer within the reaction between 2 things. Oxidation and reduction is a transfer of electrons. Something loses them, and something gains them. The The way we track it is through this process of looking at what are called the oxidation states and how they change. This one's straightforward, and then the rules for oxidation states will get a little more complicated, but the idea is the same. So notice that copper is just a solid here, which means its oxidation state is 0. Solids don't have a charge as a solid, like by themselves. Pure substances are always 0. When it goes into solution, its charge is now +2. I'm just going to write that so you can see the connection. So copper is going from a 0 to a +2 charge, which means what in terms of electrons? Is it losing or is it gaining? It's gaining. Very good, because we got to remember electrons are negative. So if I lose things negative in my life, I become more positive. So label this line as lost electrons, which we call oxidation. Or we would say that the copper is being oxidized. The silver is going from a +1 to a 0. So it's going down. There you go. So it's gaining electrons, which we call reduction.
Wouldn't it be a +2 because there's 2?
So when we list oxidation changes, we list them by the individual atom. Now you're totally right, Joel. In terms of the total number, yes. There's 2 electrons being lost, or 2 electrons are being gained, but atom to atom, you track it by just the atom itself. But yeah, total number is 2. Okay, so when we write the half reaction, we just take that thing and leave everything else out, and then we bring in the electrons. So for the oxidation half reaction, we would have, so we have Cu solid turning into Cu2 plus aqueous. Now, is it losing or gaining? Losing. So if you lose electrons, it should be on the product side. So +2 electrons. And then for the reduction half reaction, we would have 2Ag plus turning into solid Ag. And then on this one, we would add the electrons to the reactant side to show they're being gained by that substance. You can always check your half reactions for balance, because notice 0 equals 2 plus 2 and minus 2 together, right? So make sure that when you combine them, they equal what's on the other side. And that this should always equal that. Because you can't lose electrons from nowhere, and you can't gain electrons from nowhere. They have to come from something. Yeah?
Actually, never mind.
Okay, so I'm going to pour it together. It's not a super spontaneous, it is spontaneous, but it's not fast. I mean, it's not super slow either. So you're not going to see anything in the first
It's
instant.
not instantaneous.
Yeah, it's not like, bam, silver.
Maybe I knew that.
That'd be pretty cool. So I'll let it sit, and then I'll bring it around so you get a closer look once it starts going.
Yeah, mine's.
While we're letting that go, for some more smiley face. Any questions so far? Oh, just a side note. So to help you not mix up definitions, just like endo and exo, you can easily get backwards just by definition. You can, if you're a person who likes mnemonic devices, there's a common one of oil rig. When you're talking about redox, oxidation is losing, reduction is gaining. If that helps you just not mix them up. The way I choose to remember it, because it feels backwards at first, but why would we call gaining electrons reduction?
Because they're reducing their charge.
The charge gets reduced. That's how I remember it, is because the one that goes down is getting reduced. The one that goes up is getting oxidized. But if that helps you so you don't mix up, like your understanding's right, but you just mix up your definitions. Okay, so let me hold it up already so you can see. So here's what it looked like before, copper wire. It's not shiny copper anymore, right? So the silver is starting to form.
Does it form around it,
So
or
if
does
you
it just fall to the
stick
bottom?
Question,
something in
does
there,
this
break the
reaction
wire.
get hot? Or does
Not to a measurable amount.
it, okay.
It might, but yeah, not that I can tell.
Wait, so is there just silver around the copper?
Yes. Because that's where because those are the ones changing electrons from, right? Because it has to give electrons to something, the other thing has to take it, so they have to literally be.
So would the wire ever like just go away all the way?
You tell me, Grant.
What?
What do you think?
I mean, probably.
If you have enough silver to balance, right, then yep, it would be gone. Okay, we'll come back to
What
this
if
in a
the
second.
silver is like isolating the copper from the rest of the silver?
Then you shake it up.
Yeah, so I'm gonna let it grow because it gets quite pretty as it grows, and then I'll shake it so the silver falls and the wire is available for more to grow.
So you can take out the wire right now and it'd just be like more oxidized.
Say that one more time,
You
Ian.
could take out the wire right now and it'd just be like oxidized copper, right?
Yep. Well, I mean, there's silver that's shrivel on it.
Well, yeah, but
It's
if
been
you shake off
oxidized
the
inside
silver,
silver. Yes.
Silver covered copper.
Silver just replaces the wire.
Okay, for smiley face, I'm gonna give you 1 minute. It should be quick. Figure out in these two half reactions what's being oxidized and what's being reduced. Ready, go.
How many times?
Just 1 minute.
In these two both, oh, I'm gonna write them.
You can write them on your notes. Yeah, it's fine. They're already there. So just label one as oxidized and which one is oxidized and which one's reduced.
So with the Statue of Liberty, like, over the time it got oxidized, was there silver just on the outside of it, or?
No, so oxidized is just the word used for that transfer of electrons.
Well, why is it called oxidized then?
Because it's like the same thing is happening with lead. That there's a transfer of electrons when that rust is created.
Yeah, there's no silver.
So it's
But it's the same process, right?
Yeah.
It's oxidation
Like in the world around us.
and also like it's,
well, it is thermodynamically
spontaneous.
favored, right?
It's
So what did it react with? Just the air?
Yep. Okay, 3, 2, 1. If you said oxidation reduction, you got 2 smiley faces. Okay, now those ones are clearer into what's going on. When you start adding more species to a chemical equation, it can be a little trickier to track that electron movement. So what we're going to learn are about these oxidation states that help us track that movement of electrons. Now, first thing you need to not connect, in that it's the same thing. Oxidation states are not the charge. They're related to it, but it's not the same thing. That's why, just like in the last one, we write them underneath the thing instead of on top, because charges are usually listed above. Always write it below as just to help you signify that it's something different. Now, it's going to look a little confusing because I'm just going to show you the rules just so you have them. They're in your notes, but that way you know what they are. And then we'll do a practice problem that should hopefully put it together. Okay? Oh, back up one thing really quick. If by chance we were going to combine this, so these are called half reactions. If I wanted to translate it into an overall reaction, the biggest thing is you've got to make sure the electrons match. So in this case, I'd have to times this reaction by 2 and the second one by 3. So that when I combine them together, their electrons are the same. But
Can you get smiley faces from watching the video or no?
again?
Like Trevor.
Yeah, Trevor can get them. But like if you just like go home and watch.
Is that an infinite smiley face collection?
I mean, I guess if it helps you learn, I wouldn't be opposed to it, but if you just zoom through it to find all the smileys, then you know. Okay,
No way.
just to give you an idea of the difference, okay, of oxidation state versus charge. It's not the best picture. It looks better on my computer than on this PowerPoint. But what this graph is showing you, it's showing you all the possible oxidation states for every single element. So you can't really see what they are, but the dark circle, the dark part represents every possible oxidation state. So like, for example, chlorine can be anywhere from -1 to +7. Anywhere in that range. Right? Other things have very particular ones and not a big range of oxidation state, like oxygen can just be -1, 0, or -2, and that's it.
Wait,
I would think so it can be everything.
But that's where, once again, it's not its charge, because I'm glad you brought that up, Maya. What would oxygen's charge typically be? Versus that, -2.
2 minus.
Right, so oxygen is normally a -2 charge when it bonds with things ionically, but an oxidation state is something different. Okay? Alright, so here's the rules, just so you have them. I'm not gonna really, I don't even know if there's any blanks to fill in. Are there any blanks to fill in?
Does oxidation actually have anything to do with oxygen?
No.
It's like that, but like medicine.
Not always.
Well, oxygen is just like the best one, so they have to name it
Yeah,
after it.
I'm guessing because so rusting is oxidation, right, which does do with oxygen. So I don't know if that's where it originally got its name from, was because oxygen normally can play a big role in it. But like, oxygen has no role in this reaction, right?
Well, I mean, there was NO3. There was an O3.
But it wasn't really part of the process, right? So
Yo,
good observation. Okay, so here's ready. Follow along with me. I'm going to use the rules to find the oxidation state for specifically sulfur. Now, in order to find sulfur, you have to find everything else. It's a puzzle. But that's the one the answer is looking for. Okay? So the way I go through the rules is there's certain elements that have like pretty hard rules. Like they're usually this number, unless there's something to indicate otherwise. And then there's other ones that have big ranges. So at that point, it's just a mathematical relationship to make it equal whatever the charge of the molecule is. So, for example, in this molecule right here, so we have H2S. I go to my rules, because there is a rule for hydrogen. Hydrogen's rule is it's usually +1. The exception is if it's with a metal, it becomes -1. So I check, is sulfur a metal or non-metal? Good, so non-metal, so I know hydrogen is going to be +1. Okay? Now, the molecule as a whole isn't charged. So that means the oxidation states need to equal 0. Now, you list it individually, but you have to take into account the amount when you're calculating totals. So I have 2 of them. So sulfur, to make it balanced, must be -2.
Oh, I got it.
Oh, good so far?
Memorize the rules.
Kind of, yes. They're not going to give it to you. But hope you'll see as we're going, it's mostly like 3 rules that you really use mostly, and then it's just math after that. So. But yes, those aren't given to you. So. Okay, sulfur by itself. What does it need to add up to? 0, so it must be 0.
I mean, unless some of them are not.
They're always going to be the same. So, yeah, not +1 -1 +1 -1. Okay, come into here. Chlorine has a rule where it's usually -1. So if I have nothing to tell me otherwise, then I use the rule. So chlorine, I'm going to put -1. There's 2 of them. So to balance it out, sulfur must be
+2.
+2. Sorry, I realized I should probably write bigger for the camera. Okay, good so far? All right, coming to this one. All right, oxygen has a rule. Its rule is -2. Now, to help me keep track of the math, I'm going to just write some totals down. Sorry, I'm writing small again. Probably because the molecules are small. Okay, so oxygen is -2. There's 4 of them. So altogether, that's giving me a -8.
Uh-oh.
Okay? Now, if the question were, what is the oxidation state for oxygen? The answer is -2. The answer is never the total. So be careful with that when you're answering, that you're always the individual one. Okay. Sodium is part of group 1, so column 1. That's where the rules, like, there's some easiness to them. Is like, column 1 is always +1, column 2 is always +2. So I know that sodium is +1. Good. There's 2 of them, so total that would be +2 total.
In order to equal 2, so we need +6.
Very good. So sulfur must be +6. Yeah.
What's a peroxide?
Oh, good question for the exception. So a peroxide is anything
Like 2 with
like, so H2O2 is hydrogen peroxide, but it's pretty much like anything to O2 is a peroxide. So Yeah, they're like, you're not gonna see them that often, but yeah, great. You wanna write that next to oxygen's rule to remind you what a peroxide is. Any other questions so far? Okay, coming to the last one here. Oxygen is, what's its rule?
Usually
-2. 4 of them. So overall -8. Now this is where you gotta pay attention. I don't want to add up to 0 this time. I want to add up to -2. So it's another +6 situation.
Cool.
Okay, questions before we try one to kind of see how we're doing?
So you, on this question, you're only trying to find sulfur in each one.
Yeah.
Okay.
Yeah, that was like the end. Okay. You got 5 smiley faces up for grabs. Turn the page and try practice 4.9b with your table buddy. And then we'll check it for some times, okay? I'll give you like 4 minutes. While you're working, I'll bring our silver around so you get closer left too. So pretty. Sparkly pipe cleaner. Should we show these people? So it's like metal slippers.
So you're just like looking at both sides. Just like
That's kind of, that's almost probably dying over there. It's like one of those like snakes that you like have this
But very smart. Because I know it looks like nothing, right? I want to touch it. Oh, seriously. So if I just so I'm gonna whack it. Whoa! So now the silver falls off.
Is that real silver? Yeah. Can you sell it for us? Sure. What? Why don't you do that all the time then?
Silver really isn't that.
what the heck?
So here's last periods. So what happens is you knock it and then it'll keep growing and then you can knock it, keep growing until something.
You knocked out that.
This big one?
I told you to turn
It just grew a long time until. So why is the solution blue? What's going into the solution?
Copper.
Oh, wait, why did you ruin that one?
Oh, sorry. They told me to.
It'll just grow back.
Yeah, I'll leave them right at the end of it. Okay, got 1 more minute and then we'll check this problem. It's been doing it a while. Yes, and I know yours is kind of share.
Yeah, I don't know.
All right, in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
That was so satisfying.
Okay, here we go. It's like I'm trying to train people that if they do it, it's just going to get erased, so stop doing it. It's literally every day someone is going this one. Like, you can't be listening if you're going like this.
Is anybody missing a pen? Because we have like 4 back.
I know, but some people are way focused here, and I can tell they're not focused. There's a difference. Like that seems more focused, but some are like literally staring at it like this. And that's not the point of the boards. It's not to distract your brain, but to help you.
Jamie, mine is like way cooler than mine was. Look at that.
Maybe it's gonna push the button too.
What is yours?
Okay, here we go. Ready?
We're drawing the next moment.
I'm gonna go through them, but if there's any you got wrong and you don't understand why, wave your arms, say something, and we'll talk about it. Okay? All right. Fluorine has a rule. The rule is it's -1. There's 3 of them, so manganese in this situation must be +3. You get a smiley face for everybody to get right. Okay. Oxygen has a rule of -2. There's 2 of them, so that means manganese in this case must be +4. Questions? Okay. Oxygen, go with that one, has a rule of -2. There's 4 of them, so -8. Sometimes I just write it out because I do better on paper than keep it track in my head. Potassium has a rule because it's in column 1, so it's +1. Oh, I don't want to do red yet. That's our answer. So +1, there's 3 of them. Oh, okay, +3. So then all together it needs to equal 0. I did red again. So manganese answer should be +5 in this case. So questions on that one? Okay, coming to this one, oxygen is -2. There's 4 of them, so -8. There's only 1 potassium, so that's +1. Needs to add up to 0, so manganese should be +7.
That's a lot to give out.
Say what? It is.
That's a lot.
Well, so the thing you gotta remember is when you only assign 1 oxidation state, it's just telling you the state it's at currently. But then we look at how it changes to know. But yes, that means it does have the possibility of and 0. Questions on any of these? Okay, so going off what Aiden said, the big objective is now if I have an equation and the numbers aren't as easy as the ones we looked at in the beginning with our silver and our copper, write oxidation states to identify, hey, this is what's being oxidized and this is what's being reduced. Or you can also use it in terms of identifying if it's even a redox reaction to begin with. Because if you track all the numbers and none of the numbers change, then it's not an oxidation reduction reaction. It's probably a acid-base reaction or maybe a precipitation reaction. But if the electrons aren't actually moving, then it's not classified in this way. Yeah?
With the copper wire, will it get used up? Like, if it keeps like reacting, if there's enough to react?
That's the key word, if there's enough.
Yeah.
Yep. I would highly doubt I have enough because this is a pretty low molarity.
Yeah, but if it was, would it just
Yep, you would
like,
totally
the
be
wire
gone.
would be gone?
Gone completely. Okay, so let's go through and label oxidation states. Okay, so in this molecule right here, which one has a rule? Hydrogen. So hydrogen's rule is +1, unless it's with a metal, then it would be -1, so that's more the exception. There's 4 of them, so it's like +4 total. Now, keep in mind that there's 2 coppers to balance, not coppers, 2 carbons to balance it out, So each individual carbon must be -2. List them by individual elements, not the amount of elements you have. Okay, because 2 times 2 would give me -4, so it balances to 0.
We're just keeping track of like the base, like just not
Singly, yeah. Okay, good. All right, oxygen's by itself here, so it would be 0. This situation, oxygen's rule is -2. I have 2 of them, so carbon must be +4. Come in here, oxygen is -2, hydrogen is +1, which follows the rule and the balancing. So, okay, questions so far? All right, now track the change. What has changed from left to right?
The carbon.
Good, so carbon has gone from a -2 oxidation state to a +4 oxidation state, which means it has been
Oxidized.
so that is being oxidized. What else has changed?
The O2 is going to both.
Good, so the oxygen, I'm just going to connect it to 1 because it's the same, but yes, it's in both situations. So it's going from a 0 to a -2, which means it's being reduced.
Red.
Do we not have to worry about coefficients?
And then the
No.
H is just the C.
Because, so the coefficients play a role in the balancing of the oxidation states, but in the transfer of electrons, we're looking at the individual atoms and how they change. So, yeah, great question, because that's a very common thing is people would like make this a +4 as its state, which can totally mess up the tracking of it. So, any other questions on that? Identifying from a whole reaction what's being oxidized and what's being reduced. Now, if by chance you ever do it, and you find nothing is being oxidized and there's only reduction, you've done something wrong. Because you have to have both. Because something's losing, then something has to gain it. Yeah, they can't just come from nowhere and they can't just disappear. So, all right, I'm going to give you 2 minutes to try this one for another smileys.
Okay.
Ready, set,
How
go.
do the 2 minus and 2 plus group? Oh, does it just mean that it's like if it's just like a single thing and it's going to 2 plus, then is it just 2 plus?
Yes.
Okay.
Yeah, if something isn't with anything else, then it needs to add up to the charge of the substance.
Well, oxygen is for oxygen.
So the end goal is telling me what's being oxidized and what's being reduced. Yeah, no, so then the charge. It's actually faster though than it looks once you get going. Oh yeah, check the overall charge, but it is still pretty big. Do you know where they're like, not in terms of the individual seeds, those planes would count like, because if it's already balanced, if you did take them into account, your numbers would just get bigger, but the change is like the same. So this is just SH plus, this oxidation state would just be. So these are items that are either 0 or just a change. All right, you got 30 seconds.
Oh wait, reducing is gaining electrons, right? Yeah. Oh yeah, so this is being ridiculous. And then chromium.
I got 10 seconds. 5, 4, 3, 2, 1. Let's check it and see if we did it right. Alright, so going through oxidation states, because the only way to know what's being oxidized and what's being reduced. Oxygen is -2. There's 7 of them, so it's -14 altogether. It needs to add to -2, but there's 2 chromiums to make that happen. So you should have said +6. Chromium. The other ones are quite easy because they're by themselves, so they either equal 0 or they're charged, and they have a charge. So +2, +1, +3, +4, and then -2, +1. Questions on any of the oxidation states? Can't do that, you can't do the next step. I don't know. That's like you? Just insert markers. Okay, and then I noticed that chromium is going from +6 to +3, so it is being reduced. Have a smiley face if you labeled that. And then I noticed tin is going from +2 to +4, which means oxidized. So I have a second smiley face if you got that one as well. And then in this case, we would kind of say that the hydrogen and the oxygen are like spectator ideas. Because in terms of the electron transfer, they're not happening.
So would just overall equation what the electron configuration just be CR is true plus 3 as n plus CR
So there's, well, yeah, so half reactions can get a little bit more complicated when like something is connected to the oxygen, but you're on the right idea. Because it doesn't, like, it's not separated like, the other one we separated because it was in solution, like, this actually isn't separate from each other in solution, it is together in solution. Yeah, so this dissolves from whatever it was attached to, but as a whole it doesn't attach. So, yeah, we kind of, yeah, but you have the right concept. It's just a little bit more complicated. Okay, we're going to come back to that practice test question because I want to make sure we get through this. Okay, everyone stand up. Let's take a 30-second stretch break, and then we'll draw back. Let's go. You can go outside in 18 minutes. We just, like, the amount of time, if we get done, you put the bell ring, I'll let you go outside. Say what?
10 minutes with gas people.
Okay, that's when you're excused. Then we really gotta pick up the pace, that's a lot. Okay, stretch, wake up the brain. One more thing, okay? It's already 61 outside. Okay.
But look outside. Just look outside.
I know, it looks that way often out my window.
Wow, why is it white?
But it's like, look at the sky, it's like a little wire.
Okay, so.
When we see the crystals from close up now, it's like big.
After we get going, I'll bring it around again. Okay, so with this redox reaction, okay, electrons are transferring right from the copper, I'm saying it backwards, from the silver to the copper, right? And it's happening within. Something, if you haven't remembered, we've mentioned it before, but electricity is just flowing electrons. That's literally what electricity is. Our world is powered by moving electrons. That's what it is. So, right now, the electrons are moving, but all within this one system. If I separate the system, but connect it with a wire, I'm now able to use those electrons to do work. moving electrons is electricity. So that, in a sense, is what a battery is taking a redox reaction, separating it in such a way so it doesn't just happen in the beaker, but then I can actually get those flow of electrons to do the work I need. Okay, so imagine I take this, but we're going to now have 2 beakers, and then we're going to separate it, but connect it so that they can still react. Yeah?
So what does an electrician do? Like, they help electrons flow. Oh, it's like, do they like make wires or
So
whatever?
they're like chemists. Well, no, like wires.
What?
Just make pathways for the electrons to like flow, but they make them really, really complicated. So it doesn't make sense.
Yeah, but I mean, yeah, in a sense, that's one way you can think. From a chemistry standpoint, that's how you can think.
You have like 2 beakers, and then in between is just like this really complicated mess of wires.
Now, let me clarify really quick in case so you don't get the wrong image. Okay, this is demonstrating how a battery works. But inside a battery, there are not 2 tiny little beakers. But it's the concept of how it's set up.
She's lying to us. Again.
One student thought that one year that there was actual beakers inside a little battery. I don't want you to think that and then get very deceived.
How about
Okay.
we break open this battery and find
Like,
out,
I want to see the beakers.
So when the batteries get old and they like get that white stuff, is that like when the 2 mixtures accidentally like mix and then they make a precipitate?
It can be, yeah. It can be like that's something and then it makes it the way it's not supposed to.
Why do we call it a battery?
Okay, here we go, everybody. Ready? Now, the labeling, everybody. Give me your attention here. Just need a few more minutes of your focus, okay? The labeling of this process is extremely logical and makes sense if you follow the flow. Okay, otherwise you could just memorize if you want to fill your brain with memorized facts what happens. But if you really think about like how I'm going to walk through it right now, it's very logical of why this thing goes down and this goes up and this gets bigger and that gets lighter because of what's going on. Now, a few things in terms of big picture. So here's the reaction we're going to use for this battery is zinc with copper. Okay, now I could do this in a single beaker, but then it would just happen and we'd see a similar thing to what we just saw, right?
Can you do like a copper silver battery?
So some batteries, well, all batteries are spontaneous. That's their point. If it's not spontaneous, then it's not a very good battery. So yes, you can, but then you have to put in energy to make it go back.
So like the battery can be the
Does that make sense?
So because that's not spontaneous.
It spontaneously will not flow in that direction. Yeah. Okay, so these little rectangular pieces represent what are called our electrodes. Those are literal pieces of metal, like our copper wire. So I'm going to label that this one is zinc, okay, and this one is copper. Maybe label solid with it so you know like it's actual piece of metal. Okay. We connect our metals so that the electrons can flow with wires. So we use alligator clips on the metals, wire between them. So this little line, label that right there, that is your wire. So the wire connects the 2 metals together.
What flavor of wire, and why doesn't it just like take the things itself?
So yeah, so it has to be a type of wire that isn't going to react.
Rubber wires.
So it's
With-
almost like a buffer wire.
I mean, it would depend on the reaction, right? But it also, because the wire doesn't have other things around it, it's just a place for the electrons to flow through. So most wires actually would work. So now these metals are in a solution, just like this is. We don't want them to react with the solution they're in. We want the reaction to happen through the wire. So for the zinc, I'm going to put the zinc in a zinc solution. We need solutions so things can become aqueous, but I don't want the solution in metal to start reacting. So I'm going to put in this beaker some type of zinc solution. For labeling sake, we're going to use zinc sulfate, ZnSO4, but it could easily be like zinc nitrate, zinc chloride. As long as it won't react, it's good. So then what solution would I put this one in?
Copper sulfate.
Good. So then this one is going to be a copper sulfate solution. Yes, thank you, Sam. Label those as aqueous so we know. Okay. electrodes, we have our solutions, they're in their beakers. Okay? Now, according to the balanced equation, I'm going to write it down here, you can label it up there. What is being oxidized and what's being reduced? So zinc's going from Zn solid to Zn2 plus. So it's being oxidized, so label that. And that means our copper is being reduced. Okay, so oxidation means what about electrons? Losing. So on your wire, draw that the electrons, so E negative, are flowing this direction. Show them flowing from left to right. That's important to understand. That's the first thing I always do, is figure out where the electron's flowing. Step one. Then, because the electrons are leaving, something's happening to this. What happens to this when it loses electrons?
It's shrinking.
Because it's becoming aqueous. So this electrode, as time goes on, is going to get smaller. Because it's going to start dissolving into the solution. And as soon as the electrons go away, it turns into Zn2 plus. So 2 electrons leave, Zn2 plus falls off, dissolves. Now, just to clarify, do electrons have mass?
No.
Not really. So don't ever claim that the reason why this is getting smaller is because the electrons are leaving. Because electrons don't have mass.
And they do.
It's negligible in comparison.
It's negative mass.
Okay. So why is it getting smaller though, or less mass? Yeah, as the electrons leave, it turns into an ion dissolving into solution.
Does that mean that on the other side it's like sucking up copper?
Good, so then as the electrons come this way, this is now negatively charged, and because of the solution, there's copper ions floating around in here. So the copper ions start to attract and build on this electrode, making it get bigger. So this electrode decreases, this electrode increases as the electrons flow.
So is there a reverse reaction of this? Never spontaneous?
Yes, very good.
Which is why you need to put in, and that's like the thing where like electricity, when you try to recharge a battery, is putting it, like putting
Exactly.
electricity.
Yep, a rechargeable battery is you put electricity back into it to send the electrons the other way so you can do it all over again.
And since it's not spontaneous, it goes. Oh, I see. That makes more sense.
Definition-wise, when they are spontaneous, we call them a galvanic cell. So galvanic cells are always spontaneous. Next time we'll learn about electrolytic cells, and that's the definition for when it's non-spontaneous. Okay, now there's one more piece to this that is critical for a battery's function. It's what this little thing represents. Okay, label this right here. This is called the salt bridge.
Oh.
Without a salt bridge, a battery will not work. Now, here's the dilemma if you don't look at the salt bridge. Okay, so reviewing here, electrons leaving, positive going into solution. So all of a sudden on this side of the beaker, I'm going to get an excess amount of positives, right? On this side of the beaker, what are the positives doing?
Getting squished.
Good, yeah, they're coming out, right? They're going into it, which means I would have an excess negative. What's the charge of an electron? Negative. If this beaker is negative, electrons aren't going to flow towards it, because electrons are negative.
Oh,
So the salt bridge keeps the neutrality.
So how does it work?
So there's a few ways it can work. Sometimes the salt bridge comes with its own salt. They're like this, I'll bring it next time. They're like a glass tube that you fill with a salt gel. You don't want it just to fall out of the tube. And then there's positive and negative things in there, like it could be NaCl, that can flow to balance it out. So for flowing purposes, what do I need more on this side of? Good, so whatever is negative in the salt bridge bridge would flow this way. Now that negative thing could even be the extra SO4 that's already here. Because since they're connected, right, it could flow all the way across. So this could be SO4 2 minus, or it could be some other random salt that the salt bridge brought. Yeah, Aiden.
So how is this how does this work with actual batteries?
Hold that for a moment. Yes, how does this translate? Hold on for a second. Okay, so then what needs to flow that way? Good. Make sure you know that's not an electron. Electrons don't go through salt bridges. Where do electrons go?
Through the wire.
Through the wire. They don't go through the wire, that's pointless. We don't get electricity, right? So that's not an electron, it's just a negative thing
The negatively charged.
to keep it balanced. Now, technically, you can actually use something as simple as a piece of paper for a salt bridge. Because what happens to paper when you dip it in water? Yeah, the water can travel through paper, and there's positive things on, or there's negative things on this side, and there's positive things on that side. So in a sense, it could just take the excess zinc, and it would get pulled in this direction because it's negative, and then vice versa. So, gotta go to band. Okay. Questions? We still have a few minutes, but our band friends have to head out on their competition. Aiden.
Would a full wire be sufficient instead of a salt bridge, or is there any benefits?
Yeah, because, so these are ions, right? And ions don't travel across, ions need aqueous solution travel. So it has to be something, so the paper, because it has the water, or like I said, the gelatin tube allows the water, it has intermolecular forces that allow the water to capillary through it. So in a battery, it's often just a little membrane wall type thing. Chase.
So why do they use a salt bridge? Because it can bring that variable of a different salt in it instead of paper that doesn't have water,
Probably because, that's a great question, I have to think about it more. My thought of why they would maybe use something else versus just using what's available, right? Is just because it would help the longevity of it, because you have more available to keep it neutral. And you would always pick things that you know aren't going to react, because that would be very problematic, right? If you bring in a salt that happens to react with copper, you're going to get a side reaction you didn't want going on. So, but yeah, does that kind of answer your question?
So it's like a bridge that's actual salt, it will last longer because there's more ions to go to either side?
Mm-hmm. Yep. Okay, write this underneath your picture.
So if you don't have a salt bridge, does it just not, the electrons just not flow to the other
Yep,
side?
they don't float because, in a sense, they might for a moment, but then it's going to instantly become off balance, so it stops. Yeah, I think of the salt bridge a lot of in order for electricity to work, you have to have a complete circuit. It's kind of the same idea, that's what the salt bridge is doing, minus the fact the electrons aren't going back through the salt bridge. Okay, so this right here is what is called a galvanic cell or electrocell notation. So what I want you to recognize is this is just another way of showing this. So they can write an equation like we see it most of the time, or they can write it with this notation. I'll kind of explain it as you're writing. So the way you write in cell notation is you always show what's being oxidized, and then what's being reduced, and the lines kind of represent the different cells. So the double line always represents the salt bridge, and then the single line represents reactant to product, reactant to product. It's not as common on the AP test, I'll be honest, but every so often they choose to use this notation, so I just want you to be familiar with it.
Oh, so we don't have to write this notation?
No, I've never seen that, but pretty much if you saw it, I want you to understand what it's telling you.
Oh, wait, so we were supposed to
Will it be
write
on
this
ours?
now what it is? Or are we copying?
I would write the actual thing down, just so you have an example of it, but the times I've seen it on the AP test, it's in a question.
Oh, okay, like a multiple choice.
Yeah, or so instead of showing you this at the top, they would maybe write that at the top. But you should be able to look at that and say, all right, that's telling me that zinc's being oxidized, copper's being reduced. pretty much.
Is it always organized like the thing also as well?
Always, yeah, left to right. Yeah, Rachel.
So for our exam, do we have to write this out, or is it gonna be like a question we're asking?
Yeah, I won't make you write it out. There might be a question where you'll see it, so know what it means.
There might be.
It's like when
There is a question. How about that? So, questions on what it means, or can you guys kind of interpret it?
So, anode and cathode.
Oh, we'll define those in a second. So this is the name for the electrode where oxidation happens.
Yeah.
This is the name of the electrode where reduction
How do
happens.
you say the second one?
So
'Cause I
anode and cathode, is how you say them?
Because I've heard anode before, because I like that.
Yes.
But I've never heard cathode.
It's just the other side of the battery. So the electrons always flow from the anode to the cathode. The only other thing we didn't fill in that we'll get next time, so don't let me forget, is just like, we could actually maybe fill it in that. It's just some wording to what we just drew. So that when you come back to this, you're like, oh, I drew this picture, but now I have no idea how it went. This is like the story. It's just a few blanks to fill, but it's literally the same thing. So this can help you when you're like trying to remember why we drew the picture the way we did. This just puts it into a story. So I know sometimes in the moment things make sense, and then when you get home, you're like, why is that getting smaller? Or what's going on the salt bridge? What did you write this?
I remember it at home, and then the second the test gets handed to me.
Oh, yeah.
The split second the test gets handed to me.
Okay.
Here's that one too, if you want to finish out the section. That's why a lot of times you would provide right up the salt but it's actually not going to be it's going to be problematic if you see plus. Oh, I see what you're saying. It would slow the batteries, but yes, that's why actual batteries always have
Secret message. Haha, this is a secret. The secret password is peanut butter jelly.
But that probably is why, right? Is that's one of the reasons.
Yeet, haha.
Yeah, I mean, it's one of the reasons. There's a lot of things that can go wrong. But yes, definitely that would be one of the reasons even, right? Is like, if it eventually makes its way all the way over and then starts pulling and then the electrons aren't flowing how you want them to. Oh, did we not get to it last time? Okay, so we need to do just pretty much like 96 in that equation. Okay, I'll make it up that we hit that next time. Thanks, Allison. Sometimes I forget if one class gets a little Okay, I have to go meet with another teacher.
Yes.
I can probably answer one.
Okay, if we can have this one, then I can text my friend.
It is.
Okay,
This
cool.
question on the test, it was asking about
How would I?
of these different acids you made a buffer with.
Oh, okay, which one would you best buffer at that pH? So the thing you gotta remember is the buffer equation, like the pH
So,
equals the
Here, we
pKa
can like
plus
science this, right?
a log
Because
of
I've tried sciencing
the
it, I think
acid,
I'm just
remember that
way
equation?
too
So that's like the equation that tells you the pH of the buffer. So a huge factor that determines the pH of the buffer
so
is the pKa.
one of those is a strong
It can vary from that,
acid
but
and
because
or
the log of a
strong
fraction
base.
isn't
Just
ever
remember,
that
isn't
big
it
of a
like a strong
number,
acid
it
is
should
a
be
weak
close to it.
base,
So that's
or
really
strong
all we
base
do
with
is
weak
we just
acid
look
makes it
at
Yeah.
the pKa, which is the
So,
negative log of
I don't think any of
pKa.
these are strong acids, except for HCl.
Well, we just want which one is actually going to be
Oh, you're
closest
actually
to
right.
7.5.
Does that make sense?
Yeah, that's really it.
Do you remember how
Science.
Science is so
There
good.
you go.
I
You estimate the
scienced
log, you
it.
just look at the power.
Okay.
So that's literally, yeah, you just look at the power, and since the power is closest to it, I know it'd be the best choice, because then I need as minimum, like the ratio doesn't have to be like drastically different. So.
Okay, so for buffers to predict what pH they're going to be for the pKa.
Yes. Yep.
Okay.
Perfect.
not a question. It's a cool thing.
Yeah.
We were talking about like power cells and stuff. Have you looked at hydrogen power?
Not tons, no, but
Because moving an electron, right?
yes.
Pretty much hydrogen powered cars put hydrogen in it.
Yes.
And then it just makes, using chemistry, it makes water, right?
Uh-huh.
But it has pretty much a cell hooked up so the electron moves through the wires
Oh.
instead of like just
Being like a
shooting it.
combustion.
And it does, and it makes
Oh, that's cool.
electricity.
Yeah, because I've heard the idea of like, and I knew like it just made water, but I didn't know it was like, was it just a combustion reaction like gasoline, but we're using hydrogen instead of gasoline? But they separate it to actually like make the flow, so it is
literally-
electrical.
It's just electrical because they just, and then the hydrogen just moves on a different path, and then they just move the electron over.
Yeah.
And then it just makes water, and then if you've driven for a long time, you have to press a button, and it just shoots out in the water. So it's completely green, which I think is cool.
Yeah, that is
But
very
it's
cool.
super hard to store hydrogen. and stuff.
Yes, that would be the super tricky part, right? Is like,
They've got a couple of working hydrogen cars.
really?
Pretty much they're all in Brockville, which is fine.
But like public working ones?
Yeah, like you can buy them. And their tanks and stuff, like normally they're super dangerous because they're pressurized and stuff.
Yes,
But
yes.
I think it was Toyota that like figured out a way.
Because that would be my next question is like, how do you safely?
They tried blowing one up and it like exploded so fast. I guess it didn't.
Yeah.
Somehow was.
But-
Somehow the explosion happening so quickly that it didn't have any early effect. It was dangerous.
I
I
don't-
don't understand how that would make
I don't know
sense.
about-
Like the car exploded and it wasn't dangerous?
Because like they punctured the.
Or the
tank.
tank exploded?
Yeah.
I've
and I think
seen-
they like punctured it and lit it on fire at the same time.
I think it was
But it didn't
Toyota.
explode the entire car.
It didn't.
Interesting.
I think it was Toyota. They did like crash tests.
Like it would just be crazy loud, but I guess, well, and it's not a long burning fuel.
And it just.
Because I mean, that's what I do in our balloons, right, is hydrogen. And it's loud and does have flame, but it's not long, like it's instant. So that makes sense,
That's
actually.
probably why.
But yeah.
Because it just like, yeah, it'd be loud and you would have an explosion, but unlike gasoline, which ignite and like
it takes-
slowly burns. Wow, that's cool. That's really cool.
But yeah, look on YouTube, find some stuff. It's awesome.
Yeah, that's really cool.
Kristen, were you gonna do anything about question 20?
Oh yes, I thought I fixed it.
I
But I'll
just,
fix it.
should I just turn in my correction?
Yeah, so you just don't need to do that.